So we will first start with the motivation examples. Is a physical model to give a motivation to the first order differential equations, how the physical model link with the mathematics. Okay, so the motivation example. Of first order ODE. And we will use a train sliding off a frictionless table. Frictionless. It sounds very simple, right? So let's have a table. Very simple one. Very simple one. Okay. We have this table. And then we have a train. The total length of the train will be A. And then the dangling part of the table is B. So the left part over the table will be A minus B. And this is at time equals 0. So at time 0, we have this string. Total length of A, the dangling part is B, the leftover is A minus B. And we are trying to ask the question that how long the train will slide off the table. And we will start the model development, how to build the ODE here. So model development. We'll assume two things. Assume one, that the chain has the density, which is mass per length, is sigma. So we have our chain, the density is mass per length sigma. Then we also have the second one is at time t, the xt is the hangover part. So that at time t, then the hangover part will be xt. At t equals 0, x0 will be equals to b, right? Then what is the driving force for the chain slide off the table? So the driving force of the chain slide off is that Fg equals mg, the gravity, right? Then that is equals to, at time equals to t, is the slide off part is xt times the sigma, which is the density, that is the mass of the hangover part, times the gravity constant. Then the total mass is accelerated by this driving force, accelerated by this driving force, F equals ma. So this is the total mass, which is the total length times the density, right? And then it will be accelerated by the acceleration part, which is the v over dt. Okay. Okay. Well, we also know that this driving force is our Fg, so that the xt times sigma times G will be equals to A times sigma times dV over dt. Because the driving force is Fg. So we can write these equations. And we know that the sigma and sigma can cancel out. So you can cancel out the sigma part. What you can get is the dV over dt equals xt times G over A. And we also know that the dV over dt is equals to dV over dx over dt using substitution, right? So the dx over dt is the velocity. It's v dv over dt, dx. And we know that equation 1 and equation 2 are the same. So we can say that the right part, the right term of the equation 1 and the equation 2 are equal as well, because the left part are equal to each other. So that what we can do is the v dv over dx will be equals to xt g over a. So we can rewrite these equations by just putting all the v term in the left, all the x term in the right. So v dv equals xt, and we know that g over a are constant, dx. So this is our first form of the differential equations. The first order differential equations is called separable form of first order ODE. Okay. Then the question comes, can we solve it analytically for this separable form of the first order ODEs? Yes, we can. So let's do that. Okay. Okay. So how we solve it? We have now the physical model changed to the ordinary differential equations, which is v dv equals g over a x dx. And this is a separable form of the ODEs. Well, we can integrate both parts. Integrate both sides. So you can get half of v squared will be equals to half of g over a x squared plus some constant, right? And this is how we solve the separable form of the first order ODEs. It's the most simple form to solve analytically. Then we got this explicit solutions. Explicit means that the functions will be written as the independent variables. And with the initial equations, we can solve it more explicitly with the initial conditions that we know at time equals to 0, the initial conditions, right? Time equals 0, at 0 will be the dangling part, which is v. And we also know the velocity at time equals to 0 equals to 0. So we use these initial conditions to solve the solutions. And we can drive explicit solution for xt. And basically, we want to know the question in the end, how long this chain will slide off the table. That means the xt eventually will be equals to the total length of the chain, which is a, right? So we take this initial conditions that when v0 equals to 0, we have 0, so v0 equals 0, x0 equals b. We have half of g over a v squared plus some constant, so that we know the constant will be negative half g over a v squared. And we know that if we put this constant back into our solutions, we get the v will be equals to g over a x squared minus b squared. Okay. And since the velocity is a positive number, so we take off the negative part of the solutions. And we know that this velocity is as function of x and t, right? So we can get this dx. So the velocity can also write the derivative of the x as function of t, that will be equals to g over a x squared minus b squared. And you can get that, you can also do in that separatable form, dx over g over a x squared minus b squared equals dt. So it's another separatable form for the ordinary differential equations. And we can write dx over x squared minus b squared equals a over g square root dt. And this is a constant here. Okay. Probably couldn't see here. Okay, the constant here. And we can doing, so this is another separable form of first order ODE, right? And how we solve it? We can integrate both sides, right? So we integrate both sides. Both sides to get the final solutions, which is that the integration of 1 over x squared minus b squared dx equals to ln x plus x squared minus b squared equals the right side integrate will be a over g t plus some constant, right? So this you can check from the integration tables. And we can again trying to solve the constants by using the initial values. So applying the initial value to get constant c, that x0 is equals to b, and our form before is ln x plus x squared minus b squared equals g over a t plus c. So when t equals to 0, we can get that ln b equals g over a c. So we get our constant will be a over g root square ln b. Okay, so that is our constant. After getting the constants, we can get our exact solutions, which is ln x plus x squared minus b squared will be equals to g over a t times a over g ln b. Okay, so that is our exact solutions. And if we put realistic numbers inside, we can get exact time for all the chain slide off the table. If A is equals to 10 meter, B equals 1 meter, gravity constant is 9.8 meter per square second square, then we can have the total time for the chain sliding off the table, where the x will be equals to A, because that is the hangover part will be the entire length of the chain. So we get 10 plus 10 square minus 1 square equals 9.8 divided by 10 t. Right? The ln b part, the ln 1 equals 0. So we get our t equals 3.02 seconds. So with this realistic number, we know it will probably take 3 seconds for the entire chain to slide off. And this example is actually showing that how we can integrate our physical models into mathematical form of the first order ordinary differential equations. And we show a simple analytical solutions for the ordinary differential equations using the separable form. And we also show that with some initial conditions, we can solve the solutions explicitly and get the exact number for particular physical models.